Okay, everyone can hear me all right, I assume? Okay, so my name is Jose Calderon, as was just mentioned, and this is some work on improving implicit parallelism. So often when I tell people this is what I work on, I get, why are you doing this to yourself? Don't you know how many PhDs we've lost to this topic? Are you crazy? And just to give a bit of context, I think it's important to know a little bit about York. So York is a walled city. You can see there's some walls. And while it was built to keep out Scots, it actually did a really good job of keeping out the hordes of grunge rockers and naysayers of implicit parallelism during the 90s. So when I went to this man's office to talk to him about doing a PhD, and I said I wanted to do implicit parallelism, instead of going, oh no, we tried that, it was bad, he just kind of like gave me a mischievous smile and tilted his mustache and said, okay. So little did I know that it's quite hard. So Edward said the other day that it's the end of Moore's law, blah, blah, blah. So I don't need to tell you all why we're kind of looking at this again. Okay, but if you have one takeaway, so if you leave this talk with kind of one central idea, this is what it is that static analysis alone is not enough to achieve implicit parallelism. This was the main technique in the 80s and 90s. There were other ones, but this was the main thing, static analysis, parallelize your program, and hope. Okay. So what we use is profile-directed feedback in addition to static analysis to achieve some better results. So this was inspired a lot by the Harrison Singh paper in, I think, 2007 ICFP. Okay, so let's quickly review some PAR annotations. Okay, so they're a simple way to introduce parallelism in a functional program, and they're pretty cheap if you use a sparking model. Okay, and importantly for our work, they lend themselves to their use in strategies. So if you don't know what strategies are, we will go over them. But that's an important part of what we're doing. Okay, so classic kind of naive recursive fib, just to show you what pars are. If we wanted to parallelize this in kind of the obvious way, what we could do is we could give names to the recursive calls to fib, and then say here, we're using the infix notation, so we say calculate x in parallel, then do y right now in this thread, and then we're going to sum them together. The reason we do one in parallel and then one not in parallel is because we don't want them to clash immediately, right? We want the threads to kind of both get progress and then add them together. Okay, so importantly, PAR annotations also lend themselves to switching. And what do I mean by that? So this is the type for PAR. It takes an A and B and returns a B, and we just from the type signature, if everything's pure, we kind of know, okay, well, it's not really doing anything with that A. And that's because PAR is really just doing kind of a side effect of sparking off the evaluation of its first argument, but really it just returns its second argument. So we can see that as a switch. If you switch a PAR off, it just completely ignores its first argument and acts as ID over its second argument. Okay, so now, with some more vocabulary, what's the takeaway? So we're going to use static analysis to introduce PARs throughout our program, right? That's what static analysis is good at. But then we're going to use profiling data to determine which pars shouldn't have been introduced. And that's what static analysis is bad at, right? Static analysis is not good at saying, oh, this computation is going to be worthwhile, but it is good at saying this is safe, right? So we're going to try to use the best of both worlds here. Okay, so now, how do we do it? First step is higher order specialization. I used to call this slide defunctionalization, but so many people got angry with me, so I changed it. Okay, so it serves two purposes in our work. The first one is that it's necessary for the projection analysis we use, which is Ralph Hinzey's from 1995, and it helps us specialize PAR sites. And what do I mean by that? So here's a kind of typical PAR map. It's the nice high order function, the type of stuff we like, takes a function, takes a list, and then it calculates applying the function over each element in parallel. Okay, but what's the problem? Is that for every use of PAR map, we have one PAR site, right? So for all of the functions we're using with PAR map, it's reduced to one place where parallelism is introduced. And that's kind of not fine-grained enough for us. So if we do higher order specialization, we then get a PAR map for each function that we've used it over, and now there's different PAR sites for each of the functions that we call. So now, if one of the functions is expensive and it's going to be worthwhile to do in parallel, we can we can keep that parsite on and turn off the parsite for one where it's not expensive, and it wouldn't be worthwhile. Okay? So now par placement. Okay? What do we want? We want safety. So one of the limitations of this work is that it doesn't try to introduce speculative parallelism. It's parallelism based on what we know is going to be needed. Okay? So we only spark sub-expressions that are needed, and we use projections for strictness analysis. I think I already said that. I shouldn't have written that. Okay. So what's the difference between projections? So you may have kind of thought about strictness before, and the kind of classic view of strictness analysis is this. So if I present a function with a non-terminating argument, is the result of that function non-terminating? Right? And if the answer is yes, then you know that that function needs its argument. And that's kind of an idea of strict. But that doesn't really give us enough kind of control, because you can think of something like sum. Right? Sum needs its list, but then all you know is that it needs it to the first cons. But really, sum needs more than that. So projections allow us to ask that. So projections form this kind of different question. They say, if I need this much of this function's result, how much do I then need of its arguments? Right? So that allows us to express this idea of a context. So something like sum says, well, I need the full list, all of its spine and all of its elements, in order to compute my result. So that's what projections give us. So you don't have to understand this. This is how we represent projections in our compiler. The only thing I wanted to point out is that it's a lot like a type you would use to represent types, except that we have this idea of a strict lift and a lazy lift. So it's kind of it's a type, but with strictness as part of its type. Okay? So projections have this relation to strategies. If projections tell us how much of a structure do we need, and strategies tell us, please evaluate this structure in this way, to this depth, you can see there's kind of a correspondence. So one of the contributions of our work is that we show that for any projection, we can derive a strategy automatically. So that was also one of the limitations of the work in the 90s, is that they kind of had to hard code these strategies into their compiler. This one says, for any projection, we can make a strategy. Okay? So it's similar in idea to Berne's evaluation transformers, but that was limited to the ones that the compiler writer had written in. Okay? So, just as an example strategy, let's say our analysis determines a list can be fully evaluated. Okay? So a strategy for this takes another strategy that you're going to apply to the elements. It takes the list and returns unit, because its only job is to evaluate the structure. It's not trying to give you a meaningful result. It just wants to evaluate the structure to some depth. So we recurse over the list, and for every element, we use the past strategy on the element items. Okay, so using strategies, again, it's exactly like the slide before here, because we know that plus needs both of its arguments. It's a primitive that is strict in both of its arguments. So we can lift out its arguments, and because integers are already, there's no kind of depth to them. The weak head normal form is the full result. We don't have to apply like a strategy over it. We can just say, okay, parallelize it, and then we always do a seek right before the function body because of this kind of synchronization issue. Okay, so in the 90s version, what would have happened? We'd be done, and we'd try to run the program and be very sad that it wasn't as fast as we wanted it to be, and then claim that the whole idea is bunk. Okay, but in the remake, we try having the compiler do what programmers do, right? So if you've written a parallel program in Haskell, you don't just kind of think, oh, that looks like it can be done in parallel, and that looks like it can be done in parallel, and you place the parallel annotations and run it, and when it doesn't work, you give up and say, okay, no parallelism, I'm going to go back to the sequential thing. No, what do? You load up thread scope, and you say, okay, what's really going on? Let me figure out where it's useful and where it's not. Okay, so have the compiler do this. And we do it with this idea of parsite health. So not all threads are equally productive, right? Some threads do a lot of work and they really contribute to the computation, and some threads don't do much of anything. But each thread does have a unique origin in the program, and that origin corresponds to a particular par. So we can calculate how healthy a parsite is based on all of the threads that it sparked off, doing some calculation. So if we just look at how many reductions each thread does, we get something like this. So this is for the famous sum-Euler program, and it has 9 parsites as introduced by the static analysis. And for each parsite, there's loads of threads. Some of them, like parsite 3, actually has hundreds and hundreds of threads, but they all take 3 reductions, because by the time they get there, it was already in weak head normal form. It's just not a worthwhile parsite to have. So you can see, some of them have more variance, and some don't at all. So already, if you had seen this in kind of like a profile, you would say, okay, well, let me try turning off the ones that don't seem to be doing anything. And you would probably get a better speed up. Okay, so how do we incorporate the feedback? We calculate this parsite health, and then switch off the weakest one. Okay? We say, okay, you're not contributing much to this program, so why don't you just take a seat? Okay? And then we repeat that until there's no performance increase. Okay? So what's that look like? So if we have a program like this, and these are all the introduced pars, we can point to them. It's kind of like a bit string that's saying, is it on or is it off? Right? And then we iterate through until there's no more improvement. And in this is sum-Euler, we only are left with 3 pars. So most of them are turned off. So what's that look like? Well, here, for sum-Euler, it actually didn't do too bad. The static analysis did kind of give a speed up. But by switching off the pars that are weakest, we do better. Right? That's kind of the idea. We use static analysis to get this initial placement, and then we switch off things as we iterate. Queens 2, which is a program that had been written for the reduceron, based on the famous Queens program. This one, there's so much potential parallelism that when you introduce it all, you actually get slowdowns, right? And that's not that crazy. If you have enough parallelism in your program actually becomes a thread scheduler as opposed to actually computing your result. And as we go through and turn off things that aren't useful, we get back up to where we want to be. This one's not good. Okay, so what happened here? So this is a program, because often a criticism we get is like, well, what if you don't write a parallel program, right? What if you just write a program that is inherently sequential? And well, yeah, our compiler isn't magic, I'm sorry. So that's what this is, and we don't get any speed up. Okay, so it looks nice, and I hope I've convinced you there's something to the idea, but I don't want to paint too rosy of a picture. There are issues. So we've written our own compiler and our own bytecode interpreter to experiment with this idea, and if we kind of naively transfer the results of the final program to GHC and see, okay, does GHC give a speed up? It's less than ideal, okay? And we discussed that in the paper a bit. And we're not entirely sure that this technique will scale to really big programs. We still have to do more experimentation in that. So yeah, I guess I was so excited I went through pretty quick. I hope you all forgive me. So what's the conclusion? Early results are promising, but there are some issues when we transfer it to GHC. We'll likely need other forms of specialization. So the same way I talked about higher order specialization, you can think of maybe monomorphization or specialization to computation depth. There's other things that might be worthwhile. And lastly, the big kind of thing that's limiting us is that we rely on the safe parallelism. We don't try to do speculative parallelism, and for some programs like the tautology checker, that's quite a limitation, because sometimes you write programs that say, okay, we're going to have this long lazy list, and we're going to filter over it and take the first result, and you can't then, if you're only using safe parallelism, you can't compute that list speculatively, right? Because you don't know how deep you're going to go into it. So that's quite a limitation. Okay, so I'll be a little cheeky. Here are things you can ask me about. Okay, you can ask me about problems with benchmarking. I think this is a general problem. I don't have a good answer to this, but maybe we can start a discussion. What's necessary to get it into GHC? There's a lot of people here that I'd like to do things so that it's easier for me. This is bad and I should feel bad. Okay, yeah. So any questions? Yeah.
So sort of related to the second one there, but can you give us a flavor of the sorts of problems that you encounter? So I haven't read the paper yet, but I'm sure that give us the flavor of what those sort of problems are.
So there's kind of a few things. When you transfer it naively to GHC, your sequential program won't have a lot of the sharing that's necessary for the strategies to kind of do their thing. And that ends up slowing you down quite a bit when you introduce that sharing. That wasn't there in the sequential program. So I'm not exactly sure how to get around that. If you want to discuss that more, I'd love to. Yeah, I don't really know. Yeah.
So you proceed by turning off the least useful parse to arrive at the solution. And I'm wondering if this may lead you to a solution that is not optimal. So, for example, if you have 8 parse, I imagine you could just test all the possible combinations and see whether you've got the right one.
Yes, interesting that you asked that. So I have some extra slides here. If we use other search techniques, we did a paper for the search-based software engineering community where instead of kind of this informed thing where we do the weakest one, we do things like hill climbing or greedy searches. And so greedy, we kind of just go bit by bit saying, is it helpful if we turn it off or not? And then hill climbing is kind of the standard, look at the neighbors in the search space, find one that's better and keep doing that. And when we do that, a lot of times we see that the greedy actually works pretty well. But, so this slide might make you think, oh no, we don't find local maxima, we're doing pretty good. But in this one, we can actually see that if we do kind of a hill climbing, a more general thing, we do sometimes find better parse settings. But notice that, so this is number of evaluations. This is, the greedy gets there pretty quick, but the hill climbing takes a bit longer to find the better thing. So it's kind of what you would expect. It's a trade-off between how many times do you want your compiler to run the program versus how good the result is going to be. And it turns out that the greedy search actually does a pretty good job. So I did not prime him for that question, but I do appreciate it. Yeah, thank you. Yeah.
So if these are simulated parallelism results, you're assuming some overhead for scheduling a Spark?
Yep. Yeah.
Oh yeah, just what is that overhead?
Well, it's a knob that we turn. And in the paper we show kind of the results for different settings of that knob. It turns out that the bigger overhead you have, the more parse sites get switched off. And there's kind of, I forget what it is, but there's like a medium setting that seems to correlate most with the kind of realistic GHC style overhead.
Right. Yeah. It's great that you're doing this. I can't wait to see the GHC results.
Oh my, okay. Yeah.
So how expensive is each iteration while you're testing the different parameters, turning them on and off? And if it is cheap, have you considered trying to do this online?
Okay, so the first part, that's related to kind of the benchmarking issue, right? So I think all benchmark suites have this issue of like, well, are you sure that you're testing representative programs? And so for this one, we're doing kind of batch-style programs where we run the program to completion. So it's going to depend on the program itself. But which inputs you choose for that is also a variance. So it's not quite clear how to solve that problem. If you had long-lived processes, like web servers or whatever, you would have to ensure that you picked some kind of representative, standard activity for that process. So, and maybe run it for just a minute or something. I don't know. It's a hard problem. Yeah.
Okay. You mentioned trying to figure out how well it's scaled.
Yes.
And how well does this hold across like module boundaries or whatever? Like, if you were to break up your program and run this optimization on some small part, does that hold to those optimizations? Yeah. So
right now, because of the high order specialization we do, it's not modular. We could use the Hinsey analysis is a modular analysis. The issue becomes you can't test the modules individually, so you're going to have to wait till you have the whole program anyway to see how the pars are used. So that's the big problem with that. But, yeah.
You just go back to where you specialized your par map. You were saying about the higher order specialization. Did you call it?
Yes.
So of course this kind of thing happens in Vite. GHC does this kind of thing quite a lot. And usually you do it just by the little idiom of writing a non-recursive par map with a local recursive one and just inlining it bodily.
Oh, okay, right.
Right. So would that? My sense is that would probably do exactly what you need, and the cases when it won't work is when you're somehow calling with a more complicated, you're building up a function that you're passing, but then that's not going to work for you either. So would it be, I mean, of course, it's a little extra burden on the program, but only on the programmer who writes these higher order functions.
Yes.
And then you just say, inline this. Would that do enough for you, do you think?
Yeah, I think it might. Yeah.
It's a very simple way to achieve your goal.
Yeah. I think that would get most of the way there. Yeah.
Can I ask one sort of follow-up, which is also about specialization? So one of the tricky things with this granularity stuff is I thought when you got some sort of divide and conquer calculation, you want to sort of switch off the pass, single pass site when you're sufficiently deep in the tree.
Yes.
And it's a little tricky how to it's hard to see how you could completely automatically. Do that. I wonder whether you had any thoughts about that.
So our idea is, let's say you have some recursive computation, as you say, and you want to specialize based on depth. Well, what you'll actually get out of that is two functions that have independent parse sites, and because maybe it's really the leaves that are the expensive part and not the top level thing. So there'll be just two new pars that this iterates over. Mm-hmm. I think the bigger issue with things that are like lazy and GHC is some proxy for that depth. I don't really,
right. And even knowing that you need two functions.
Exactly, yeah. So, well, actually, for that part, Colin and I have, sorry about this. Okay, we're almost there. Okay, so Colin and I have the idea that this will actually help us determine that. Mm-hmm. So if you see something that has a long tail, mm-hmm. that hints at, maybe it's a worthwhile computation until you're recursing down a bunch. So we think the information is here. How do we tease it out of it? Mm-hmm. Is the question.
Cool, thanks.
Okay. I did a good job? Yeah? Yeah? Okay.